Section 6.4 we talked about a little bit last time. The whole idea in this section is that we're going to work with proportions. And all a proportion is it is a equality statement about ratios, two ratios that are the same. And we had some wonderful theorems here that talked about the ability to flip the fractions upside down and to cross multiply and to switch the diagonals. And we recognized that all of those created equal proportions to what we started with. And so we're going to actually see the ability to do that within particular problems depending on how we view setting them up. All right, so here's our first question. Jim found that after working for 9 months, he had 6 days of vacation time. If he accrues vacation time at the same rate, how many days would he earn in 2 years? So we have to consider whenever we're looking at these problems, what is being compared? And there's always at least 2 things that are being compared. So what are we making comparisons of in this problem?
Vacation days to months working.
Fabulous. So that's one of them. We're comparing the number of days working to the number of vacation days we get. What else? Actually, number of months. You're right, yeah. Something else, though.
How much you would earn in 2 years.
Yeah, a comparison of like today versus 2 years from now, right? So those are the 2 things we're comparing. As we make the decision about comparing, you can do a comparison so that one is the numerator, the other is the denominator. That's one comparison, like a ratio. The other comparison is that you're going to have to put it across the 2 equal signs. So one left-hand side is going to be one thing, right-hand side is going to be another. So here's where it might look different. So let me show you one of the options, and then I'll show you a second one so you can see what I mean. We could compare our number of days of vacation compared to our number of months of working as a fraction like this. And then we could compare on the sides of the equal signs our now compared to our later. So everything that's happening now is on the left, everything that's happening later is on the right. This would be one way to set up the problem. So if we set the problem up like this, somebody tell me what fractions I'm going to get, what values inside my fraction. Okay, so he has 6 days now. And how many months has he been working? 9 months. Okay, what are we going to do later? X. We don't know the days. That's kind of what we're trying to find. Over 24 months. Excellent. So we do need to make sure that the units match in order for this to work, right? So we can't put like 2 in there because that would be 2 months, not 2 years. All right, so what would I do then to solve this problem? You got it. We're going to cross multiply. So I'm going to get 9x equals, what's 24 times 6? I agree. Good. I mean, I cheated because I looked at my paper, but yes, I agree. All right, 144. What would we do next? You got it. We're going to divide by 9. And what do we get for x? 16 days. Okay, let me show you another way to set up the problem, not because I care how you set the problem up, but because I want you to recognize that there's more than one way to do it. And it's kind of interesting because the other option of what I'm going to do actually will show you why those theorems are true. So let's say instead of comparing days to months the way we did, we're going to compare the days to months across the equal sign. So days on the left and months on the right. We could do that. There's nothing wrong with that. Then the other comparison we're making, which was the now compared to later, would be the fraction itself. So how many days does he have now of vacation? 6 days. How many days later will he have? X, because we don't know, right? How many months has he been working now? 9 months. How many months will he have been working at the other point in time? 24 months. Now, without looking or worrying too much about days, months, and the setup itself, just look at where the numbers are. It is the same cross multiplication. Compare just where they are. Tell me what's different. What is different, actually, in the physical numbers where they are?
The 9 and the x.
The 9 and the x. It's a diagonal switch, isn't it? Well, that's what it said I could do with the third theorem down here, right? I can switch diagonals. I mean, legitimately, we do it all the time. And so then, of course, you're right. Yes, we get the same cross multiplication because switching diagonals is a legal operation, if you will. We're allowed to do that. So I'm not going to finish solving the problem because, of course, it works out the same way. Let's try the next one. On a city map, a rectangular, that should say park, not part, park, has a length of 4 inches. if the actual length and width of the park, oh my goodness, it was twice in there said part. Is it right on your paper? Oh, no, it's not. Fabulous. Are 500 feet and 300 feet respectively. How wide is the park on the map? 1 out of 3 is not good. Okay, well, we'll fix it later. All right, what are we comparing? Inches to feet. So like really what we're comparing is like the map to real life, right? So we're comparing the map to real life. Do you want to put that as the fraction or as the two sides of your equation? The fraction. Okay. So this would be, and I'll write it the way that Haley said it. It's inches compared to feet, not because we're trying to say inches and number of feet, but it's the map compared to real life. What else are we comparing? Length and width. So if we've set up 8 inches and feet as we have, then length and width have to be the two sides of my equation. Okay, what is the length of my park in inches? What is it? Is it 4? Okay, 4 inches. What is the length of my park in feet? 500 feet. That's the real life value, right? What is the width of my park in inches? X. We don't know that. And you don't have to use X. You're welcome to use any other letter that you so choose. Don't make it a T or something because then it starts to look like pluses. But, you do have choice. Okay, so X is my inches in this case. What is the width of my park in feet? 300 feet. Now what will we do? We will. What are we going to get? 500? 500 on one side. I'll leave my new units off until the end. And then 500x rather, sorry. And then 1200, yes. And then what? Divide by my 500. What does x end up equaling? 2.4. Now, we are going to leave it as 0.4 and not turn that into a fraction. Do you have any idea why we might do that? No, we could write the 4 as a fractional, the 0.4 as a fractional part. It really has to do with the ruler itself, right? I mean, when we look at a ruler and we're looking at decimals and fractions, decimals tend to be a little bit more accessible on a ruler. So it seems to be a little bit more realistic. And we're talking about doing something with a ruler on a piece of paper. So could we write it as a decimal or as a fraction? We could, but 2.4 inches seems quite realistic to leave it that way in terms of the context. You got it, even though decimals don't exist yet. You're right. All right, this is a fun one. It's different. Kierra and Dora work 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that each of them are paid according to the time they spent. How much should each one earn? Do any of you have fairness as one of your strengths? None of you do? It's also called consistency. Nobody has that? You might? I do. I have consistency. Fairness is one of my strengths. It's a catch-22, really. It's not so always good. But anyway, I want to make sure that I'm treated fairly. All right, let's take a look. They work a different amount of time. So the idea being that they should get paid for how much they work and not just split it evenly. Make sense? Okay. So there's a little bit of a weirdness to this one, though, because of the comparisons that are made. So tell me, what could we compare? We have a couple options. What could we look at being compared in this problem? Okay, we've got hours compared to what? That's hours and what? Pay. What else? The two people. Right, we got Kierra and we've got Dora. Okay, everybody good so far? Okay, let's see what we know. Do we know how many hours Kierra worked? Yes. We do. What does she work? 3.5. Are you guys okay with me writing 3.5 even though decimals don't exist right now? Okay, fabulous. How many hours did Dora work? 4.5. Fabulous. How much is Kierra paid? We do not know. How about Dora? We do not know. So what are we going to do? One of them gets to be an X. I don't want Y. Oh, you guys, somebody's caught it. Oh, this is wonderful. Yeah. All right, so Yeah, I mean, it's y. It's another variable. I mean, I get that. But if we have two variables in the problem, we're going to run into problems being able to solve it. So one way to do this problem, and there's a second way I'll show in a second, is to recognize that if one of them works x, the other one, not works, but if one of them gets x dollars, the other one gets what's left over, which is 176 minus x. Okay, let's solve the problem from here, and then I'll show you one other way you could do to set the problem up, okay? All right, so we're going to cross multiply, right? All right, so one of my diagonals is going to be the 4.5x. What do I have to be aware of happening on my other diagonal? There's multiplication with distribution, right? So we need to take the 3.5 times the 176. What's that? 416? Is that good? Okay. And then I also have to do the 3.5 times the negative x. So I have negative 3.5x. Now what? Okay, I'm going to add my 3.5x because you guys told me to. What is 4.5x plus 3.5x? It is. It's 8x. So 8x equals 616. Whoops. There we go. And then divide by 8. What is x? 77. Now, let's go back to the question that was asked. The question actually asked is how much should each one earn? What did we find out so far? How much one of them, specifically Kierra, earned. So Kierra earned $77. What about Dora? 176 minus 77, which is 99. This is a totally cool, legit way to do the problem. Okay, nothing wrong with it whatsoever. But there is one other way to do the problem, and Andrew almost started going down that path earlier, so I want to do the other option. Andrew, do you remember what you were about to tell me before we went down this road?
I took it the way of going, well, how many hours of work divided by the total number of what they got paid each hour.
And the key word I want to hit on is the word total. Instead of comparing the two girls to each other, you could compare one of the girls to the total amount. So I can leave my hours and pay just like they are right now, but I'm going to leave Kierra on the left, and instead of putting Dora on the right, I'm going to put the total amount on the right. So Kierra still worked 3.5 hours. Okay? But how many hours were worked total? 8. We still don't know how much Kierra made, but how much was made total? 176. The nice thing about this is that we don't have to worry about distribution. There's no plus or minus x involved. That's kind of nice. The harder thing about this is to recognize the comparison is not the comparison of the two people. I mean, the comparison of the two people will be a little bit more natural, but this one involves a little bit simpler arithmetic. Okay? If you cross multiply, you're still going to get finding out, that x is equal to 77. You still have to go back then and find out that Dora's is the 176 minus the 77. You still get $99. Okay? So a couple different thoughts on that one. At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? This is a two-step problem. What kind of comparisons do you see right now? Teachers to students, I'm going to actually write that as the fraction. Teachers to students. This is the teacher-student ratio that we're referring to. What else are we comparing? Or any thoughts?
The ratio to the total number.
Yeah. So we've got a ratio on one side, right? That's the 1 to 30, 1 to 25 that we've been talking through. But the other side is the actual number of, we'll say people, because it's students in one place and teachers in the other. Do you guys see that? Okay, and we've got two teacher-student ratios, so we need to leave the 1 to 25 ignored for the moment. We'll come back to it. Let's take the 1 to 30 teacher-student ratio first. So teachers is 1, students is 30. What am I going to do on the other side? X. X is the number of teachers, right? What about the students? We have 1,200 students. What in the world is this going to allow us to find? The number of teachers they already have, right? Okay, great. All right, we're going to cross multiply. We have 30x equals 1,200. And then what? Divide by 30. What does x equal? Did you guys say 40? Okay. 40 teachers, right? 40 teachers is what we have right now. Now what am I going to do with that 1 over 25? We're going to do the same thing again, but what's going to change? Right, you're going to have a 25 here instead of a 30. You still have the same number of students. You don't have the same number of teachers, so I'm going to call it y. This is not the teachers that we currently have. It's the teachers we want to have, right? Okay, and then I've got 1,200 on bottom, right? Okay, we're going to cross the multiply. I've got 25y equals 1,200. Then what? Divide by 25. What does y equal? 48. 48 what? Teachers needed. That's a good way to describe it. Now, this is the total teachers needed. That's not exactly what I was asked. What was I actually asked? The additional ones I need to hire. So the answer to the question I'm asked is actually 8. I need 8 additional teachers. Any questions on that one? Okay. Whoops. My screen is all messed up. Okay, there we go. Mary is working with measurements and writes up the following proportion. 12 inches to 1 foot, equals 5 feet to 60 inches. How would you help her? Okay. Did she do anything right? She did do something right. Have you ever guys heard of the sandwich method?
Yeah, you like say something good and then you say what
Yeah.
the truth is.
Yeah, is the idea of starting out with something good, tell them what they screwed up on, and then something good at the end. Yeah. Kind of like lessens the blow of them making a mistake. Yeah. So did they do anything right?
Yes.
They did. They did. That's fantastic. What did they do right? Yeah. The individual ratios that they created, these individual ratios are correct. Agreed? Yeah, so that's good. So first, the idea, at some point in the idea, whether it happens first or not, I kind of think you should do it first. But somewhere in there, you want to commend them for the fact that they've got correct ratios. So the ratios are correct. Okay, so yay, well done, great job. All right, but not everything is all well done and good job. So now what is incorrect? Yeah, the comparisons are not being made the same across the equal sign, right? So the up and down, the vertical comparisons are good. They're correct. The ratios are. But the equation across the equal sign is not being compared, apples to apples, right? Or in this case, inches to inches. It's not being compared in the same way. So the issue is that you would say one ratio needs to be what? Flipped or switched or something like that, right? It needs to be flipped. So that the numerators, or you could say denominators here, it doesn't matter which one you want to use, but the numerators are both the same. I'm going to use word units. And I'm going to put and so are the denominators, or so will, we'll say and so are the denominators. So they sort of set it up half right. I mean, that's really what they did. They set something up half right. We need to make sure that the comparisons are being made both across the equal sign and vertically up and down inside of the same fraction. Okay, we have one more problem. Are we good with this one? Okay. Amy. Amy's friend told her the ratio of boys to girls in her classroom was 5 to 6. Amy was surprised that her class would have only 11 students. What would you tell her? Okay, so pause for a second. At face value, is what Amy's friend or whatever Amy's saying possible? Is it possible with this values that she really could have 11 students? Yes. So it is possible she could have 11 students. For whatever reason, they hired too many teachers, not enough kids came to class today, whatever. I mean, could there be 11 students? Yes. So that's something to be aware of, is that there could be 11 students. And in some scenarios, that might make sense if you were dealing with a smaller school district, a less than, expected enrollment, or maybe you had a classroom that was for special needs or something like that. 11 might actually be a number that makes sense. So this is something to be aware of first. So kind of the issue is that it could be 11 kids. It really could be 11 kids. And there may be a reason why we'd have to justify that, but we don't know because we're not Amy's friend, okay? All right, we could be this Amy's friend and this Amy's friend, but we're not the Amy's friend in the problem. All right, so what else could be going on with this context as it's given? She's adding the 5 and the 6. Okay, keep going. You guys have said good things, but we aren't quite there yet.
Like her friend said, basically there's 5 girls for or 5 boys for every 6 girls.
Okay. So let me ask the question differently. If we don't really have 11 kids, how many kids do we have? A multiple. Why? Explain some more, Haley.
It will be like groups of 11 almost. So like, I don't know how to describe it.
Okay, so you're thinking something like if you had, I'll kind of write this down here, if you had 5, is it boys or girls? Boys, okay. 5 boys, we'll just put B, and you had 6 girls. So if you had one group of 5 boys and 6 girls, this could just be one of the groups of 5 boys and 6 girls. So maybe you have another 5 boys and 6 girls, in which case you'd have how many kids? 22. What if you had another one? You could have 33. That'd be an awfully large class. That'd be rough. Let's hope that Amy's friend does not have 33 kids. 22 might actually happen, though. I could see that, yeah. Okay, so do you know why this is happening? I mean, you're explaining it in one way. There's another way to think about it that's more along the lines of this particular content in the section that we're working in. Let's say for a moment that we had the 33 kids. How many boys would that be? 15. How many girls would that be? What can you tell me about 15 over 18? They will both reduce to the 5/6, right? So when Amy's friend is giving her the 5 to 6 ratio, why would she be saying the 5 to 6 ratio instead of saying maybe the 15 to 18 ratio? What did she do? She reduced. That's it, right? The ratio that she's giving may be a reduced ratio, right? Okay, so the 5 boys to 6 girls may be a reduced ratio. So she may have, and we'll use the 22 now as an example because that's probably the realistic one or the most realistic one. She may have 22 kids, which would be 10 boys and 12 girls, right? Because the 10 to 12 ratio equals the 5 to 6 that she was told by her friend. Does that make sense? All right.